So everyone, can you hear me clearly? Can someone please confirm with message? Okay, thank you. And online students like YouTube live students, can you hear me clearly? Again, can someone please confirm with a message so that we can start the session? YouTube live students. Okay, okay, thank you for that. And if you like find any issues in the session, or if there's any kind of issue in video, or like or the Zoom live session or anything like that, just inform me as soon as possible. So even you can contact me. Like these are the options. You can contact me through this number if you find any issues in joining the session, or if you like face any kind of issues, or if you need any guidance after the class or something like that, you can just message me through this number, and I will provide you the number of my coordinator so that if you need any assistance, you can contact my coordinator. For any emergencies when I'm teaching, sometimes I'm not answering any calls or anything like that. So if there's an emergency like that, you can contact this number. So let's start the session, and good morning for everyone. And as you know, I'm Jandalela Ananda. I think most of the students joined the last lesson. So I think everyone knows the our target. I'm Jandalela Ananda. I'm an advanced level physics tutor and an Olympiad trainer, but we decided to do this seminar series to assist students in O levels, especially English medium, because there were no seminars for English medium students. So that's why we decided to do this series. So in the last session, we finished, as I remember, in the last session, we finished mechanics. Today we have to do other areas, and this may not be the last session. I may be doing another session if required. Specifically today I'm targeting things like electromagnetics, geometric optics, and some of the other requirements mentioned by the students. And everyone please go to the group. I think everyone is in the group, and fill that Google form where you can request any suggestions that you have. Even while doing the class, I will check those suggestions and do what is possible within the time given for the class. Clear? So if you need anything to be done, or if you need any support, or if you need to know anything else, just mention it in the like in the Google form, and you can contact us for anything for related to O level or after O levels. When you need guidance on deciding subjects or anything like that, you can contact us. So I'll start with the lesson. Today I'm gonna start with electromagnetics. So let's start with electromagnetics. I think a lot of students find that area difficult, so I decided to do that part first. I think everyone has their note. Note is available in the group, uh, and now it was uploaded to the Zoom chat too, so you can get the Tute through the group or from the Zoom chat. Okay, you have all the options available. And I think maybe in the last part of the Tute, you can find the electromagnetics lesson. So this note is specially made out of your textbook, okay, but with some additional questions, okay. This is just like a short note created out of your textbook, okay. You can quickly go through the note and like revise all the theory parts that are required. That is the main target. Okay, so let's start. Electromagnetism and electromagnetic induction. අපි මේ කතා කරන්නේ විද්‍යුත් චුම්බකත්වයයි විද්‍යුත් චුම්බක ප්‍රේරණයයි ගැන. So we know that a magnet creates a magnetic field, okay? A magnet creates a magnetic field. So if we have a magnet like this, if we have a magnet like this, it creates a magnetic field. It creates a magnetic field like this, okay? It creates a magnetic field like this, and this magnetic field comes out from the North Pole and returns to the South Pole. That's how a magnetic field behaves. And when talking about the behavior of a magnetic field, another thing that we should understand is there are two types of magnetic fields, or else there are two types of magnets. They are electromagnets and permanent magnets. That means you have permanent magnets, okay? You have permanent magnets. That's something we usually know. You have seen permanent magnets, but the problem is even when you're like shipping containers in the harbor, you can't use a permanent magnet for that, okay? You can't use a permanent magnet for that. You first take a plate, okay? We use a plate and we keep it close to the container. Then we activate the magnet. Then it sticks with the magnet. Then we move it first to somewhere else. Then we release it. So we must have the ability to create and also stop this magnetic field. For that we use electromagnets. So electromagnets is producing a magnetic field using electricity. Clear? Electromagnetism is producing a magnetic field using electricity. විද්‍යුතය පාවිච්චි කරලා චුම්බකත්වයක් හදන එකට තමයි විද්‍යුත් චුම්බකත්වය කියන්නේ. So that is the most useful scenario in our industry. Okay, that's used mainly in the industry. So now we have to understand this magnetic field is a result of moving charges. Okay, this magnetic field is a result of moving charges. When charges are moving, okay, when charges are moving, it creates an magnetic field. It creates a magnetic field. Clear? So basically, so as you know, gravity is a result of mass. So it creates forces on mass. Likewise, magnetism is a result of moving charges. So it creates forces on moving charges. That is the idea. So if a magnetic field is a result of moving charges, what is a moving charge? Moving charge is a current. Moving charge is a current, right? If magnetism or magnetic field is a result of moving charges, then current is the moving charge. When charge is moving, we call that current. ආරෝපණ ගමන් කරද්දී අපි ඔකට කියනවා ධාරාව කියලා. So this current should create a magnetic field. So we use Maxwell's cross-screw law or the right-hand grip rule to find the direction of this magnetic field. So usually we can use the thumb of our right hand and we can place it in the direction of the current. We take our right hand and we place the thumb of the right hand towards the direction of the current. Then from other fingers, we get the direction of the electromagnetic field. So usually moves around this wire like this. Clear? It goes around this wire like this. Why? When there's a current, if my thumb is moving like this, then electromagnetic field is like this. Electromagnetic field, it moves like this. Clear? So when we have a current carrying wire, there's an electromagnetic field forming around that wire. විද්‍යුත් චුම්බක ක්ෂේත්‍රයක් එයාගේ වටේට මෙහෙම හැදෙනවා. Clear? Okay. Now what? Now, as I said, this moving charges or a current produces a magnetic field, and a magnetic field can create forces on current again. Clear? Magnetic field can create forces on current. So for that, you have this very simple wait, I'll go to my note. You can go to your note. You can go to your note page. Yeah, check page 81. Page 81. Check page 81. We have a system like this. Okay. We have a system like this where we can create a magnetic field. We use a magnetic field like this. You can find the north here and south here. So it creates a magnetic field like this. Here, it creates a magnetic field like this. Then we use two plates like this. We use two plates like this. And we keep a conductor on top of that. We keep a conductor on top of that. Give me a second. I'll try to get the knot again to my smartboard so that it would be easy to explain. Okay, now we have the note. Okay, so this system, I'm talking about this system. It's easy to explain now. Let's use this system. So this was available in your textbook. Okay, this was available in your textbook. So what happens is we create a magnetic field in this direction. Clear? We create a magnetic field in this direction from north to south. Clear? Now when we put this switch, it creates a current through this path. It creates a current through this path. Now, can you tell me what would be the direction of the movement of this pin? What would be the direction? Quickly tell me. Quickly tell me. And coordinator, can you please put the PDF again in the WhatsApp group? Some students are requesting. What would be the direction? Quickly tell. Quickly mention. And you know the law. You know the law. Quickly mention in the Zoom chat. What is the law? What is the name of the law that you can use for this to find the direction of this pin? Anyone? Nice. Fleming's left hand rule. Fleming's left hand rule. What is Fleming's left hand rule? How do we get Fleming's left hand rule? You have to know these things, okay? It's available in your textbook. So, when you get your left hand, okay, when you use your left hand, and when you place your fingers like this, then this, then this, when you place your fingers like this, middle finger represents the direction of current. Middle finger represents the direction of current. Then this one index, it represents the direction of magnetic field. Then thumb represents the direction of the force. So here, as you see, battery is placed in this direction. Here, battery is placed in this direction. So current will be moving like this and this and this. So my middle finger should go through the direction of current. My middle finger should represent the direction of current. And magnetic field is from north to south. Magnetic field always moves from north to south. That means north to south. My current is going in this direction and magnetic field is from north to south. Magnetic field is from north to south. Then thumb represents the direction of the force. So direction of the force is this. That means this pin will move in this direction. Clear? This pin will move in this direction. Clear? So that is the idea. That is the idea. That is Fleming's left hand rule. Clear? We call this Fleming's left hand rule. So now what are the applications of this scenario? There's a lot of applications. Okay. Why do we use brass rods? Okay. I'll explain that again. Why do we use brass rods in this one? There's a question. Why do we use brass rods? Here, I mean, anyways, the basic idea is to make sure that current is flowing. Because here, this pin should be freely moving on top of this one. This pin should be freely moving like this. Okay. But at the same time, current should be passed through this pin. Okay. Current should be going through this pin. Clear? At the same time, there must be current moving through this pin. So brass rods, it's a good conductor. It's a good conductor. So it allows current through this one. But again, it's mechanically strong. It has a strong structure so that this pin can freely move on top of that. Is that clear? Is that clear? You can't use just loose wires or anything like that for this. Yeah, nice. Okay. And online YouTube live students, if you have questions, please ask. Okay. Everyone, if you have questions, please ask. So what are the applications of this scenario? And first of all, I'll try to give you some very simple questions. Usually we use this symbol to represent when something is going towards the board. So if you see this mark, that means the magnetic field is going towards the board. And if you see this mark, that means magnetic field is coming out of the board. Okay, this is the standard rule that we use. Now tell me, if you have a magnetic field moving in this direction, that means north is here, south is here. Magnetic field usually goes from north to south. Yeah, sure. There's a request to do the applications part also. Yes, I will definitely do the applications. First, I will teach the theory parts quickly, and then I will move to applications and I'll explain everything. So if you know the theory parts, if you have no issues with the theory parts, then you can see in the last part of the electromagnetics lesson, you can find questions. Then you can quickly try the questions until I come to the required applications part. Definitely, I'm going to do the application parts properly. Yes, that's what many students requested, but you have to be a little good with theory before I start the applications part. That's why I'm doing this. But if someone finds this easy, until I return to the application part, you can quickly do the questions in the last pages of the tute. Okay. So there's a current, there's a wire with a current moving in this direction. Quickly try to find the direction of the force on this wire. Quickly find the direction of the force in this wire and quickly mention it in the Zoom chat or YouTube live chat. And again, there's a magnetic field going towards the board. There's a magnetic field going towards the board. This is the magnetic field. We usually use B, symbol B to represent the magnetic field. Then there's a current carrying conductor with a current moving in this direction. Find the force, direction of the force on this one. Quickly find these two and give me the answers as soon as possible. This is question number 1 and this is question number 2. Yes, I'm getting answers. Thank you. Okay. We have some answers. Then we'll see. First of all, middle finger towards the direction of current. Middle finger towards the direction of current. Index towards the direction of magnetic field. Then thumb gives me the direction of the force. Then you should see when middle finger is moving this way, when index is moving in this direction, thumb moves towards the board. Thumb moves towards the board. That means the force is towards the board. That means this wire will be pushed into the board. Clear? Wire will be pushed into the board. Clear? This wire will be pushed into the board. That is the direction of the force on this wire. Is that clear? Just mention whether it's clear or not. Please mention in the chat. I mean, let's keep this active, okay? give me the answers and ask questions. Okay, quickly try to answer the questions. Then I know that you understood. Then I can quickly move on. Okay, we can keep this efficient if you reply. Okay, so you got that? The direction of the motion. Current moving in upward direction. Magnetic field moving in this direction. Then force is in this direction. That's Fleming's left hand rule. Clear? Fleming's left hand rule. Then here, what about this? What about this? Current moving in this direction. See, current moving in this direction. Magnetic field moving into the board. Magnetic field moving into the board. Current moving in this direction. Magnetic field moving into the board. Then what? Then what? Then thumb provides me the direction of the force. Thumb provides me the direction of the force. So the direction of the force is this. Someone has requested for the tute. You can see in the YouTube live one in the description, in the YouTube live chat, in the description, in the YouTube live session, you can find a drive link which you can find the tute. Just let me know whether you got the tute or not. Student who asked for the tute, check the YouTube live description of the video, and quickly let me know if you find the tute or not. So, got it? Clear? Current moving in this direction and magnetic field moving into the board. Magnetic field moving into the board. Then force is towards this direction. Okay, you can find it. Just give me a second. Are you in the group? Give me a second. I'll make sure that the tute is available. Okay, I checked that. So for online student who ask for the tute, you can find the tute. Okay, it's available there. Okay, I mean in the YouTube live description, you can find the tute. But if you find it difficult to find the tute, or if it is not working on your laptop or anything like that, quickly contact this number. Put a WhatsApp message to this number. He will add you to the group. Not 702544701. He will add you to the group quickly and he will send you the tute too. Okay. It's available in the Zoom chat, but if you like, it's available in the Zoom chat, in the group, in the YouTube live description, it's available everywhere. But if you find anything difficult, just contact my coordinators. We will arrange you everything. So, is it clear? Current moving in this direction, current moving in this direction, then magnetic field moving into the board, then force is in this direction. That's a nice question. How do you represent that the force is moving towards the board? This is the symbol. See, it's it's not only about magnetic fields. If anything moves into the board, you can mark it like this. If anything comes out from the board, you can mark it like this. So you can write F equals this. F is going towards the board, across, across. You got it? You got it? The student who asked the question, you got it? That's how you mark a force moving towards the board. Clear? And this is a very common application of this scenario. This is a very common application in the of this scenario. What? Loudspeaker. In a loudspeaker, what happens is actually these loudspeakers create sound waves, right? Loudspeakers create sound waves. So we all know that sound waves are a result of, okay, sound waves are a result of moving particles, right? You already know the waves lesson. You already know the waves lesson. Sound waves is a result of moving particles. That means in a loudspeaker, what should happen is these particles, these air particles should be moving like this as a wave. Okay. That means someone should push these air particles. That is sound, right? Sound means moving air particles. We know that, right? Sound means moving air particles. Clear? So someone should push these particles in this direction. So the job of a loudspeaker is to push particles, push air particles in a pattern. Clear? Job of a loudspeaker is to push air particles according to a pattern. Clear? Okay. When I'm speaking, according to the pattern of my speech or the pattern of my voice, these particles should be pushed by the speaker. So to a speaker, we provide an electric signal. Okay. What happens is when we connect it to our mobile phone or laptop, our laptop sends electric signals which aligns with the music. Assume that we are playing a music using our laptop. What our laptop just sees, it sends electric pulses, which is equal to the pattern of the music. So we can see pulses moving through this one. So we can see you have a current carrying wire here. See, you have a current carrying wire here. It carries current. Clear? It carries current. And again, so it is usually going through the south pole. Okay, you have a current carrying wire like this around the south pole. So based on the current sent by laptop, the current in this one changes. Current in this path changes. Then you can see there's a magnetic field from north to south. Now what happens? When there's a magnetic field from north to south and when there's a current, it creates a force. Now, according to my electric pulses, it creates a force on this wire. It creates a force on this wire. Now what happens? When we create a force on these wires moves like this. So the current changes. Then due to magnetic field, when current changes, the force changes. So when the force changes, how this is moved, how these two coils are moved in this direction, it changes. Based on that, how this diaphragm is moving, it changes. When the movement of the diaphragm changes, how it push particles changes. Then when the pattern of these particle changes, it changes the sound. That is the usual mechanism of a loudspeaker. Is that clear, everyone? Is that clear? That's how a loudspeaker works. Just mention in the chat. Is that clear? We we send a changing current. We send a changing current to this circuit from our laptop, maybe a music. It changes the current going through this conductor. Now we have a magnetic field. Now there's a magnetic field and there's a current. That means there's a force. So based on my current, it creates a force on these beams. And based on the force, this diaphragm moves. out and in. This diaphragm moves out and in. And if my current signal represents a music, okay, if our current signal represents a music, this diaphragm will move according to that music and it will create a nice sound. That is the whole idea. Clear? Is that clear, everyone? Just mention in the Zoom chat. Yes, you can use left hand rule, but I think it's not required to use the left hand rule here because this is a 3D image. This is a 3D image. When I explain you the motor, you will understand. I will properly explain you the motor. Then I'll again explain this part. Then you will properly understand how to apply the left hand rule for scenarios like this. But this is the simple idea. We send a varying current. It changes the force acting on these beams. It changes the motion of this diaphragm. That is the idea. Clear? There's a question, how do we use Fleming's right hand rule? Yes, I'll explain when I move to Fleming's right hand rule. So for now, it's Fleming's left hand. Okay, now we are going to learn about the DC motor. Okay, next one is learning about the DC motor. So we know the parts of the DC motor. We have the armature, that means a coil. Then we have magnetic poles. This is the system. I'll explain you. I can use a video for that. I'll properly explain this part because a lot of students find this DC motors part hard. Okay, try to understand this properly, okay? Try to understand this properly. I will explain very slowly because if you understand this one, you will understand a lot of things related to magnetic fields, okay? Especially related to the direction, things related to the direction, okay? So here, now, I'm going to create a motor. I'm going to slowly explain the motor because if you understand the motor properly and everything related to the motor, then you understand almost everything in magnetics forces. So we have a wire like this. We have a magnetic field and a wire like this. We have a magnetic field and a wire like this. So this is north, this is south. And there's a current going in this direction. There's a current going in this direction. So left hand rule, my current moves in this direction, current moves in this direction, magnetic field goes in that direction, then force is in this direction, upward direction. Current goes in this direction, magnetic field in this direction, then force upward direction. Now there's a force in upward direction on this one. Clear? See, current, magnetic field, then force in upward direction. There's a force acting on this wire. There's a force acting in upward direction. Now, next wire, current moving in to the board, magnetic field like this. So, current moving in this direction, magnetic field this, then force this. So, the force on this wire would be in downward direction. So, there's an upward direction and an downward direction. There are two forces. Due to these two forces, it tries to rotate. it tries to rotate. Now, we have connected this end to a battery. Positive side of the battery, we have connected this end to the positive side of the battery. We have connected this end to the negative side of the battery. So current goes like this and comes like this. Current goes in this path and returns. Clear? Okay. Now, we have connected this to the positive terminal and this to the negative terminal. Now it rotates. Due to these forces, it rotates. Now there's a problem, okay? Now there's a problem. Initially, when they were creating the motor, they just connected two wires. You connect the positive terminal to this, negative terminal to this. Now when they rotate, positive terminal is still connected to this guy and negative terminal is still connected to this guy. Now see what happens. Now see what happens. It rotates due to these forces, it rotates. Then positive terminal is still connected to this one, negative terminal is still connected to this one. Now current is moving like this. Now current is moving like this. Now you would find the issue. Now now apply Fleming's left hand rule. Current moving in this direction, current moving into the board, magnetic field in this direction, current moving into the board, magnetic field in this direction, then force downward. On this guy, force is downwards. Then what about this? Current moving out, magnetic field in that direction, current, magnetic field, force in this direction. Now there's a force on this guy, there's a force in this direction, on this guy, there's a force in this direction. Now what happens? Now what happens? Previously it rotated like this. Previously it rotated like this. Now again, due to these forces, it would rotate like this. Now you should see the problem. Now if you keep your motor like this, it would forever rotate like this, then this, this. So if you connect this motor to your car, okay, if you connect this motor to car, your car will never go anywhere, okay? Your car will never go anywhere. Why? It would rotate 180 degrees, then again 180 to the other side. 180 to this side, clockwise 180, anti-clockwise 180, clockwise 180, anti-clockwise 180. It will keep happening forever, okay? It will keep happening forever. Clockwise 180, anti-clockwise 180. You will never go anywhere, okay? So it is pointless to use this motor, okay? That was the initial problem they had with the motor. When they were creating the motor, this is the initial problem they had with the motor. So they understood the problem is when this one rotates, still I have connected wires here. Due to that reason, current going through the loop in the same direction. That is the problem. So they so they understood this problem happens when it turns 180. This problem happens, but if we can change the direction of the current, when it turns 180 degrees, then still it will again rotate in the same direction. Clear? If when it turns 180 and when it tries to move in the other direction, if I can change the direction of current, then it will keep rotating like this. So they had to figure out a method without connecting wires. They had to figure out a method so that they can change the direction of the current every 180 degrees. For that, they use something like this. Instead of connecting wires, they connected to a system like this. They connected two commutators. Commutators in the sense just two metal plates. Two metal plates. Then to provide current, they used brushes. Without connecting wires, they used brushes. And to make sure that to provide current, they used brushes. See, they use brushes. These positive terminal and negative terminal are brushes now. Now you should see what happens. Now current goes like this. Then it rotates. When it rotates, not like in wires, not like when you are using wires. When it rotates, see, now this commutator touches this one. See, every 180 degrees, see, every 180 degrees, initially this commutator was touching this one. Now after 180 degrees, this commutator will touch this guy. So every 180 degrees, who's connected to the positive terminal changes. Every 180 degrees, who's connected to the positive terminal changes. කවුද මේ ධන අග්‍රයට කනෙක්ට් වෙලා තියෙන්නේ කියන එක වෙනස් වෙනවා. Who's connected to the positive terminal changes. Due to that reason, there's a current flowing continuously. දිගටම current එකක් ගමන් කරනවා. Clearද? There's a sorry. Due to that reason, the direction of the current changes every 180 degrees. Due to that, it will keep rotating forever in the same direction. So that's how they created the motor. This is the, like, we can call this the invention of the motor. Is that clear? Is that clear? Just mention in the chat, Zoom chat and the YouTube live chat. See how nice that invention was. I mean, physics was built like that. Okay. Physics was built like that. There's a small problem and we come up with a very simple solution to get rid of that problem. That's how physics was created. Okay. So tell me, did you understand? Just mention in the Zoom chat and the YouTube live chat quickly. Nice, nice. So this is the basic idea. That's how they invented the motor. And what is nice about this system is, I will talk about it later, but I will just mention. First of all, they had a problem like we have the motor, okay, we have the motor with ourselves and motor is rotating, and but motor is rotating like this. Motor is rotating like this. It moves, it returns. It moves, it returns. It was a problem. Then they figure out a method like this. They figure out a method. Let's use commutators and brushes to provide the current so that I can change the direction of current. I can change the direction of current. Then they came up with the motor. That's how they invented the motor. Then all of a sudden, this is something extra. All of a sudden, Faraday thought that, okay, when we have a magnetic field and the current, this thing rotates. All of a sudden, Faraday thought, so then what if there's a magnetic field and a force? Will it create a current? Will it create a current? It actually happened. That's how they invented the turbine or the dynamo. So here we have provided the current and it rotates. Then next they thought that let's not provide a current, let's provide a motion. Let's rotate this one. Let's rotate this loop. Will it create a current? It actually did. It actually did. That's how we invented the dynamo. That's how we invented the turbine. And that's how you get electricity today. Clear? That's how you get electricity today. See how simple things get connected and simple ideas get connected to come up with an optimum solution. See how nice it is. Clear? Clear? Is that clear, everyone? This is the behavior of a motor. So what is the energy conversion of a motor? What is the energy conversion of a motor? Energy conversion of a motor is we use electric energy and we create a mechanical energy using that. Clear? We use electric energy and we convert that electric energy into mechanical energy. That is the energy conversion of a motor. Now we are going to talk about electromagnetic induction. විද්‍යුත් චුම්බක ප්‍රේරණය ගැන කතා කරන්න යන්නේ. We are going to talk about electromagnetic induction. What is electromagnetic induction? Now you should understand it, okay? Now you should understand it. Electromagnetic induction is a simple concept. Okay, electromagnetic induction is a simple concept. The idea is just like I mentioned, if we can provide a current and a magnetic field, then it will rotate. So if I can rotate it, will it create a current? It actually did. That's how that is electromagnetic induction. So electromagnetic induction is basically when there's a motion, when there's a motion, and when there's a magnetic field, it can create a current, something like that. When there's a motion and when there's a magnetic field, it can create a current. So Fleming's right hand rule. So just by reversing the Fleming's left hand rule, okay? Just by reversing the Fleming's left hand rule, they created Fleming's right hand rule. That means Fleming's left hand rule was for when you know the current, okay? When you know the current and when you know the magnetic field, you can find the direction of the force. And now we provide the motion. We provide the motion. And we provide the magnetic field. Then how can we find the direction of the induced electromagnetic field? Sorry, induced electromotive force, or else how can we find the direction of the current? How can we find the direction of the current? Clear? That is the idea. So try to find now there's a magnetic field going towards the board. There's a magnetic field going towards the board. And there's a conductor moving like this. Try to find the direction of the current. Try to find the direction of the current quickly. If I explain you the right hand rule, this is the right hand rule. How? If this is the direction of the current, middle finger represents the direction of the current. Sorry, the thumb represents the direction of the motion. Index finger represents the direction of the magnetic field. Then current can be taken from the direction of the middle finger. Here, current can be taken from the direction of the middle finger. That is Fleming's right hand rule, and it's really simple. Why? It's just the opposite of Fleming's left hand rule. So you can find the Fleming's right hand rule. It's by just reversing the Fleming's left hand rule. So here find the direction of the current, and here also try to find the direction of the current. There's a magnetic field in this direction. This is question number 1. This is question number 2. There's a magnetic field moving in this direction. And maybe there's a wire. There's a wire moving like maybe moving like this. There's a wire moving like this. Find the direction of the current. Give me the answers as question number 1 and 2. Quickly give me the answers. What is the answer for question number 1 and what is the answer for question number 2? I need some more answers. And YouTube live students and also Zoom live students, everyone. Question number 1 and 2. And if you're done with these two questions, you can find the questions at the end of the tute. You can finish them too. Okay, we'll try to get the answer. First one, magnetic field towards the board. Magnetic field towards the board. Motion, movement upwards, then current in this direction. First of all, find the right hand. This is Fleming's right hand rule, so you have to use the right hand. Then current moving, sorry, force or the motion movement is in this direction. Magnetic field into the board, then current moving in this direction. Here I think we have a problem, right? You see, movement in this direction, magnetic field in this direction, then current should go into the board, okay? So I can't keep a conductor like this and create any kind of a current. My conductor should move like this. If my conductor is this, if my current carrying conductor is this, if it is like this, and if it is moving like this, then I can create a current. How? I use the right hand rule. It is moving upwards, see? It is moving upwards and magnetic fields in this direction. Then current will be in this direction, see? Current will be in this direction. So current will be going to the conductor in this direction. Current will be going to the conductor in this direction. So I can't keep the conductor like this and get any kind of a current. Okay, why? According to Fleming's right hand rule, current should go into the board. With this motion and this magnetic field, current should go into the board. Board එක ඇතුළට තමයි අනිවාර්යයෙන්ම current එක යන්න ඕන. Is that clear? Is that clear, everyone? Others? Is that clear? Okay. Okay. Nice. So here we are going to create the dynamo. And as you saw initially, can you remember that in the motor we had a problem like that? In the motor we have had a problem that if we do not change who's connected to which wire. Okay, if every 180 degrees, okay, if every 180 degrees, if we are not changing the direction of current by using commutators and brushes, then my motor will rotate like this. So here also, when this one rotates, current direction of the current will change. So if we need a current in the same direction, then again we have to use commutators and brushes. But in our actual systems, we don't need current moving in the same direction. So we just connect One wire continuously to the red one, this wire continuous to the blue one. See, we have connected, we have this wire is continuously connected to the blue one, and this wire is continuously connected to the red one. So we are not changing the connection, okay? So we are not changing the connection. So just like in the motor, when we are not changing the direction, it will change the direction of the current. Clear? If we are not changing the connection, අපි connection එක වෙනස් කරන්නේ නැත්තම්. Clear? If we are not changing the connection, who's connected to which commutator? If we are not changing that thing, the direction of the current will change. So it will move like this. Clear? It will move like this. I will explain you again. Initially, when we were doing the motor, when we were working with the motor, if we do not change the connection like this using commutators, the direction of the rotation will change. Direction of the rotation will change. So even in the dynamo, if we don't use something like this, okay, if we don't use something like this, if we keep rotating in the same direction, the direction of the current will change. So if we don't need to change the direction of the current, we have to use something like this. But in our actual dynamos, we don't need our current to be in same direction. That's what we call alternating current. We like alternating current in our current networks. In our distribution lines everywhere going through Sri Lanka, we like to have alternating currents. So due to that reason, we don't create a setup like this to change the direction of the current every 180 degrees. Instead, we just connect one side, we connect continuously to one side, other side we connect continuously to the other wire. So since we are not changing the connection every 180 degrees, direction of the current changes. Direction of the current changes like this. It becomes positive, it becomes negative. It becomes positive, it becomes negative. Is that clear? Is that clear? I mean, it's just what happened in the motor, same happens here. In the motor, if we are not changing the connection, then the direction of the motion will change time to time. And in the dynamo, if we are not changing the connection, direction of the current will change time to time because motion is continuous in one direction. Is that clear? Just mention in the Zoom chat and YouTube live and ask whatever the questions you have because this is a very important part. Understanding it up to this level is more than enough, but it's better if you can ask whatever the questions you can have and clarify all the doubts you have. Quickly mention. Did you understand? Okay. Okay, you need me to explain the dynamo again. Others? Okay, I'll repeat it. This part is usually difficult to understand and this part is not necessary to understand completely, okay? But I think it's easy to explain this using the motor. That's why. It's like this. Uh, Give me a second, I'll check whether we can use a nice video for this. Okay, I'll explain that again. Okay, check this one. Check this one. So, this is an alternating current. See, alternating current means the direction of the current changes. Clear? Alternating current means the direction of the current changes. Direct current is the direction of the current does not change. This is the difference between alternating current and direct currents. Now, you take this system. Again, there's a loop. There's a magnetic field and there's a loop. Okay. Now see what happens. See, when it rotates, okay, when it rotates, the blue one is continuously connected to this one. Red one is continuously connected to this one. Yeah. Now you should understand this thing. Uh, okay. Understand this thing properly. I'll use right hand rule. I'll use right hand rule. Now, I'm talking about the red side, okay? I'm talking about the red side. Now, red side is moving upwards. See, red side is moving upwards. Clear? Now, red side is moving upwards. When red side is moving upwards, okay? When red side is moving upwards, magnetic field is from north to south. Magnetic field is from north to south. Red side moving upwards. Magnetic field from north to south. So current goes in. Current goes in. That means current goes like this. Current goes in. And blue side going down. So current goes like this. Now in this loop, current goes like this. So if I have a galvanometer connected externally, if I have a galvanometer connected externally, current will go like this, come like this, and it is connected to this and come like this. See, now this is the path of the current. Why? When I use right hand rule, this it is rotating like this. So the red side is moving upwards, magnetic field in this direction, north to south. So current goes in. So current goes like this then comes. So it goes in this path in the galvanometer. Is that clear, everyone? Is that clear? Nice. Now see what happens. Now the system rotates. Now the system rotates. So you can remember now initially current was going in this direction. Okay. Galvanometer was connected here. Now when it turns 180, blue one comes here. Blue one comes here. Now what happens? Now what happens? Now try to understand what's happening here. Initially red one was moving upwards. Clear? Initially red one was moving upwards. Now the blue one is moving upwards. Okay, when it turns 180 degrees, now the blue one is moving upwards. Now see what is happening. Now we have the galvanometer like this again. I will explain that again. We have the galvanometer like this and like this. Now see, now blue one is moving upwards. Why it is rotating like this? So now here blue one is moving upwards. Again right hand rule. Blue one moves up. Magnetic field in this direction, north to south. Current goes in. Current goes in. So current moves like this. And red one moving down. Why? When it is rotating like this, red one moves downwards. So magnetic field, this movement downwards, magnetic field, this movement downwards, magnetic field in this direction, movement, red one moving down, then current comes out. That means current goes like this. So now current goes like this, like this. Then from the blue one is connected to this. So in the blue one, current goes like this. That means current goes like this. And current out comes out from the red one, and red one is connected to this one. Here, it goes like this. See, red wire, current comes through the red wire to this one, and it is connected to this wire. So it moves like this. Then current returns to this one, this cage. Then that cage is connected to the blue one, and current goes like this in this blue one. Is that clear? Is that clear? Nice. Now you should see initially in the galvanometer current was moving in this direction. Now what happens? Now in the galvanometer current is moving in this direction. See, since this plate is always connected to the blue one, and since this plate is always connected to the red one, every 180 degrees direction of the current changes. Clear? Every 180 degrees direction of the current changes. That's why you get a pattern like this. See? That's why you get a pattern like this. That's why you get a pattern like this. When it rotates, the direct magnetic field always in this direction. So when it rotates, direction of the current changes time to time. See, you get something like this. See, why? Blue one is always connected to this one, red one is always connected to this one. But time to time, who's moving up and who's moving down changes every 180 degrees. So every 180 degrees direction of the current changes. See, when it moves like this, current changes. Clear? Now it keeps moving. When it keeps moving, try to understand properly. Magnetic field always in same direction, but now blue one is moving upwards. See, now red one starts moving upward. Initially blue one was moving upwards. Now red one is moving upwards. So the direction of the current changes. See, direction of the current changes. That's why. So if you need to get rid of this thing, what should you do? You use brushes like this. You use brushes like this. Then you get something like this. See, why? Every 180 degrees, who's connected to which brush or who's connected to which commutator changes, just like in motor. Just like in motor, every 180 degrees, who's connected to which commutator changes if you have a system like this. So if you don't need negative current, if you don't need a negative current, you can use a similar system similar to the motor. Here, you can use a system similar to motor. So here, with a system like this, every 180 degrees, who's connected to which commutator is changing. Clear? Is that clear? Okay. Did you understand that part? Just mention in the Zoom chat and live chat. Because it's important. That's why I use a video, images, diagrams, and all to explain these parts. In A-level classes, we use, in A-level classes, we only use smart boards. Always we use smart boards because in A-levels, we have like, even in Olympiad classes, we have like some content 10 times difficult than this. So that's why we usually use smart boards. We can use videos, we can use images, diagrams, and all to explain. Can you please mention YouTube live students and Zoom students? Just mention whether you understood or not. Why it becomes negative and positive, like kind of stuff. Everyone, cool, cool. Okay. And there's a question like in ChatGPT, they mention something else. In ChatGPT, they tell that Dynamo is gives us a DC current. Just go with your textbook, okay? Because ChatGPT always talks about latest technology. So when we are doing engineering stuff, I'm an electronic engineer myself. When we are doing engineering stuff, we go search ChatGPT because we need the latest stuff, okay? But for O levels, it's not we don't have the latest technology or latest trend or latest knowledge in our textbooks, okay? So you have to trust your textbook and go with your text. Okay. That's why that is the reason because when we talk about the dynamo today, then it's a different story. But if your textbook tells that the dynamo provides an alternating current, then okay, then go with that. Okay. ChatGPT you can keep for later usage when you are an engineer or something like that. For now, believe the textbook. Okay. What type of questions you can get from this part? I have explained almost everything here. So, taking the directions, a small explanation about why current is alternating, a small explanation about why DC motor will keep moving like this if you don't change the direction of the current. What is the use of these commutators and brushes? What is the reason to use that? Things like that, theory questions like that, they can ask. Okay. How to find whether it is moving clockwise direction or anti-clockwise? They have to give you. Okay. In a dynamo, they have to give you the rotation direction. I'm just answering the questions. So did you understand the concept of alternating currents and the dynamo and all? I'm not taking a lot of time. I can take like 2-3 more hours and explain how the dynamo works because we have created dynamos by ourselves. We have created motors by ourselves. So I can dig deep and teach you everything related to motors and dynamos. Okay. Even in A levels, we teach a lot about dynamos, and even in engineering, I have learned a lot about dynamos. So I can take 5 more hours and explain you dynamos. But first we have to focus on O levels. So I will do what is relevant for O levels only. Okay. If you need to learn anything after that point, then feel free to contact me. Okay. Even in A levels, we learn a lot more than this. But for O levels, this level of knowledge would be enough. Okay. Mega anta karagatta meti. Okay. Then talking about the light microphone. Microphone. Can you remember what happened? Okay, what happened when you got a motor? When you got a motor, and instead of providing current to the motor, when you rotate the motor, what happened? Just mention in the Zoom chat. Instead of providing current to the motor, if you rotate the motor, what happens? Quickly mention. Nice. Current will induce. Current will induce. That means when you get a motor and instead of providing current, when you rotate the motor, it will act as a dynamo. It will produce current. So same goes with the loudspeaker and the microphone. Loudspeaker was all about you provide a current and due to that current, this diaphragm moves. And the mic is all about I speak. When I speak, this diaphragm moves. When that diaphragm moves, this coil moves. Now there's a coil moving and there's a magnetic field. Now there's a coil moving and there's a magnetic field. What happens when there's a magnetic field and when there's a movement? It creates a current. So this diaphragm moves based on the pattern that I'm talking. Then this coil moves based on the pattern that I'm talking. And due to that reason, due to this magnetic field, a current will be induced, and that pattern of that current will be equal to the talking pattern of me. Okay. My talking pattern will be matched with the current induced here. Why? Because when I'm speaking, this diaphragm moves, that means this coil moves, that means the movement of the coil changes with my voice. When there's a coil moving and when there's a magnetic field, it will induce a current. So a current will be induced, and that current will be similar to the pattern, speech pattern of myself. Is that clear? Is that clear, everyone? Then this is the bicycle dynamo. This is the bicycle dynamo. And you should see small differences here. In the bicycle dynamo given here, what is the difference? In the bicycle dynamo given here, what is the difference? If you see here, the magnet is rotating and the coil is stationary, something like that. I mean, it doesn't matter, okay? What is required is the change in magnetic field or a movement. So if you keep the magnet around and rotate the coil, or if you keep the coil around and rotate the magnet, still you will get an induced current, okay? So to induce a current, what requires is the change in magnetic field. You can take this change in magnetic field, okay? You can take this change in magnetic field by keeping the magnet around and by rotating the coil, or keeping the coil around and rotating the magnet. In both ways, you can get the current. Clear? You can get a current. What requires is not who's inside, who's in the middle. That doesn't matter. What is required is you need a change in magnetic field. The magnetic field will change when the coil is rotating or when the magnet is rotating. Is that clear, everyone? Two wires come out in the figure, but in the bicycle only one wire. It's because it's from inside. It's connected to the negative of your bicycle motor. That's why. So is that clear? Is that clear, everyone? Is that clear? Quickly mention. And anyways, you don't have to be worried about the O-level examinations, okay? What matters in the end of the day is what you do in A-levels or what you do after O-levels. But at these days, give your maximum possible. Give your maximum possible these days. Why? I mean, in O-levels, okay, what we check is not your physics ability or your science ability, your science, maths ability. That's not what we are seeking. It's what we are seeking is the endurance. Okay, how hard a student is willing to work. Okay, how hard a student is willing to work for their targets. Why? For A levels, you need a lot of endurance. For A levels, you need a lot of dedication. So that's why for A levels, we choose students you from O levels. Okay. So basically, these days, don't worry about like if you haven't done much or if you can't understand a lot. Yes, it is a mistake happen from your side, maybe if you may haven't worked from beginning or something like that. But what matters is if you are willing to put everything aside and work these days, work as much as possible and try to go for good marks. Okay. That means if you are willing to put a lot of hours to get rid of whatever the mistakes that you have done And if you are willing to work a lot, then that's what matters. Because in A levels, especially in science, I'm teaching A level physics. So what we see is what you need is not intelligence. You don't have to be really intelligent to do maths or physics in A levels. What you need is a lot of discipline to work and a lot of dedication. The student who has a good dedication can outsmart everyone else. So these days, improve that dedication. Okay, use this time to improve your focus, improve your dedication. Okay, try to put more hours. If you work for 8 hours yesterday, try to work 9 hours, and tomorrow. Then the day after tomorrow, try to work for 10 hours. Why? For O levels, it may not be necessary. Sometimes you will get anyways get good marks. For some students, it is really easy. So for some students, they will anyways get good marks. But what is required is to build that endurance so that you have the capacity to work for long hours if you do A levels or if you go for any engineering or medicine degree. So these days, use this time to improve your endurance and dedication. Okay, that is the fundamental requirement to improve in anything. Okay, so next part, last part of the electromagnetism, transformers. When when do we get the interval? Yeah, I'll be giving the interval at 10 p.m. I'll finish electromagnetics now quickly. Then I'll give the interval at 10 p.m. Okay. So next, transformers. Transformers. What is the simple idea behind transformers? This system, it's easy to explain with this system. Okay. When you consider this system, what happens is we create a change in current here. Okay. We create a change in current here. Due to that change in current, what happens when we what I mean we can explain it like this. I mean, this is a rough explanation. You don't need this kind of explanation for all levels, but I'll briefly explain you what is happening. When you create a current in this loop, okay, when you create a current through this loop, due to that current, we know that the magnetic field occurs due to the current, right? We know that. Can you remember we use right hand rule or the Maxwell's corkscrew law to find the magnetic field created by the current? Can you remember? So current itself creates a magnetic field. Is that clear? Current itself creates a magnetic field. When a current moves through a coil or a wire, it creates a magnetic field. Can you remember? Explain put a message in the Zoom chat quickly. When there's a current going through a wire or a coil, it will create a magnetic field. Can you remember at the beginning we learned that? Quickly reply. Okay, so when there's a current going through this loop, it will create a magnetic field, and this is a soft iron core. This is a soft iron core. That, or we can use this one also. When I create a current, okay, it will create a magnetic field, and that magnetic field will go through this soft iron core. Now, when you consider this coil, okay, when you consider this coil, there's a wire, there's a wire, there's a magnetic field, there's a magnetic field. Ah, when that magnetic field is changing, it will show a value here. It will induce a current. So first of all, quickly respond. This was available in your textbook. Okay, I'll take some time and explain you this slowly, or else you won't understand this. Tell me, this was available in your textbook, so I expect the answers quickly. What happens when I put this switch? What happens when I put the switch? What happens to the reading of the galvanometer? Quickly respond. What happens to the reading of the galvanometer when I put the switch? Yes, galvanometer moves. Galvanometer moves. See, deflects to right or left. What happens when I keep it on? I on this one, I turn on this one, and I keep it. I turn on this one and I keep it. What happens? When I turn on this one and when I keep it, what happens? Quickly, it comes to the normal. Nice. It's come to the normal. See, there is no deflection. There is no deflection when it is turned on continuously. What happens now? Now, if I suddenly turn off, what happens? What happens if I suddenly turn off this one? Yeah, suddenly current goes in opposite direction. The galvanometer deflection goes to the opposite direction. Then what happens when I keep it turned off continuously? What happens when I keep it open continuously? Yes, nice, it stops. Nice. Then what is the reason? It's like the motor or the dynamo. Can you remember? Okay, can you remember in a dynamo who created, I mentioned this, okay, I mentioned this before. Who creates a current? Who creates a current? Magnetic field or change in magnetic field? Why do we need to rotate the dynamo? Why do we need to rotate the motor? Or what do we need? Why do we need to rotate the magnet? Why do we need to rotate something? Why do we need to rotate something? Why can't the dynamo create current when we are not rotating it? Why can't this create any current when we are not rotating this? Because current is a result of current is not a result of magnetic field, okay? Current is not a result of magnetic field. Current is a result of changing magnetic field. Is that clear? Current is not a result of magnetic field. It is a result of changing magnetic field. Clear? Ah. So here to change the magnetic field, what we do is we rotate the magnet. Here to change the magnetic field, what we do is we move the coil. And here to change the magnetic field in a transformer, what we do is we turn on and off switch. Why? When we turn on, it quickly creates a current and that current creates a magnetic field. But when I keep it on, the magnetic field is there, but it is not changing. When the magnetic field is not changing, this coil will not feel any change. When there is no change, there is no current. But when I quickly turn off this switch, then quickly this magnet will be turned off. That means magnetic field will quickly change. It will quickly change. That change of magnetic field is felt by this coil. So due to that, a current is induced. But when I keep it turned off continuously, then there's no magnetic field and it is not changing. The magnetic field is not changing. When the magnetic field is not changing, then there won't be any current here. මෙතන කිසිම ධාරාවක් දකින්න හම්බ වෙන්නේ නැහැ. Magnetic field එක change නොවන විට. Let me know, is that clear? Is that clear? So what to create a current, what we need is not the magnetic field, we need the changing magnetic field. Is that clear? That's why when I turn on, it quickly changes the field. But when it is kept turned on, magnetic field is there, but it is not changing. But when I turn off, it quickly changes the magnetic field. When I keep it turned off, there is no change. So to create a current through that, to send a current through this galvanometer, what we need is not the magnetic field, we need the change in magnetic field. Students, is that clear, everyone? Is that clear? Mention in the chat. Nice. Nice. So this is the exact model of a transformer. Okay, this is the exact model of a transformer. We have the one coil here and we have a soft iron core. Why do we need a soft iron core? Usually magnetic field goes through a soft iron core. So that magnetic field created by this guy is felt by this guy. Then it creates a current. It creates a current. Okay. This guy changes the magnetic field. So it creates a magnetic field like this. And that magnetic field is felt by this guy and it creates a current. But as I mentioned, what we need is not a magnetic field. What we need is a changing magnetic field. So easiest way to change the magnetic field continuously. Okay. If we need to change the magnetic field continuously, easiest way is to connect an alternating current source here. When you connect an alternating voltage or an alternating current source, that means alternating current means changing current. See, can you remember? Alternating current means changing current, current which moves like this. When the current changes like that, current changes like this, magnetic field changes. When the magnetic field changes, it induces a current here. Okay. So we have two equations like this. NP of Ns equals Vp of Vs. That means number of rounds, number of loops in the primary is proportional to the voltage in the primary side. I will do some questions, then you will understand this properly. Then number of loops in the secondary is equal to the voltage in the secondary. Okay. This is the basic law of a transform. Number of rounds in the primary is proportional to the voltage of the primary. Number of rounds in the secondary is proportional to the voltage in the secondary. Clear? So due to that reason, we have step up and step down transformers. What are step up and step down transformers? So you should see, you will understand this probably when I do questions. When the secondary number of coils is higher, due to this equation, when the secondary number of rounds is higher, secondary voltage is higher. That means you give a small voltage and get a higher voltage out. That's what we call a step up. And when the primary coil number of primary coils is higher, number of primary rounds is higher, primary voltage is higher. Number of primary rounds is higher, primary voltage is higher. Then you get a higher voltage. You give a higher voltage and get a smaller voltage. You give a higher voltage and get a smaller voltage. We call that step down. We call that step down. So you have step up and step down. It entirely depends on the number of rounds or number of loops available. Okay, number of loops available in the wire. Clear? If you have more wires in the secondary, more loops in the secondary, it's a step up. If you have more loops in the primary, it's a step down. Okay, you will understand it properly when we do some questions. Then there's an energy equation. As we know, what is the law that we consider as the fundamental law of physics? Which conservation? Which conservation? Something very fundamental about physics? Which law? Tell me. Any physics people? Any physics people? No, I'm not asking the fundamental law of current. Fundamental, something very fundamental about physics. A very fundamental law related to physics. Nice. I got the answer. Conservation of energy. Conservation of energy. This law is really fundamental. That means whatever happens in the world, usually it happens according to the conservation of energy. That's why when I rotate the dynamo, I put some mechanical energy. It turns into current electricity. See, it turns into current electricity. When I give some current energy, it turns into mechanical energy. When I put some current, it turns into mechanical energy. That's that's what happens in the motor. I provide the current energy, it creates a mechanical energy. It rotates. See how nice it is? See. So the idea here is whatever the thing happens in nature, it usually follows conservation of energy, but nuclear things doesn't follow conservation of energy. You will learn these things in A levels, okay? Again, please raise your hand if you're doing A levels science. Anyone planning to do science for A levels? Yes, you will learn a lot more in this path. Okay. I train A level science, A level physics. Then again, I train Olympiad physics. If you continue in that path, maybe A level physics. Then maybe after that, maybe uh, Olympiad physics. You will learn a lot about physics. People, raise your hand. Who's doing like science for A levels? But what matters is what you like. Okay. I mean, we teach all around Sri Lanka online and physically. So we see now a lot of students like to do science throughout the country from everywhere. There's a lot of students participating in all the physics seminars that we do, not in O levels, I'm talking about A levels and Olympiad. I mean, whenever a country is evolving, we need more science people involved. Why? Because that's where we invent stuff. Okay, so conservation of energy. Conservation of energy. So this is the conservation of energy. Can someone tell me, do you know P equals VI in current electricity? Power equals VI. Do you have that equation? Quick to reply. P equals VI. Do you know that equation? Okay, you know that equation. Then it's really easy. Why? VP IP means there's the voltage in the primary, in the current in the primary. So power VP IP means power in the primary. You provide a certain power to the primary. You provide a certain power to the primary. So when you provide a certain power to the primary, that power is transferred to the secondary. And according to the conservation of energy, the full energy that we produce here, if it transfers to the secondary, it should be equal to the power in the secondary. Power in the secondary side. The power in the secondary side is VSIS. Voltage in the secondary side and the current in the secondary side. Is that clear? So power input equals power output. This is a conservation of energy equation. Clear? මේ ශක්ති සංස්ථಿತಿ සමීකරණය. This is conservation of energy. Power input equals power output. Clear? Or energy input equals energy output. VPIP equals VSIS. And you will learn how to use these equations in the upcoming questions. So I'll give you the interval. You can take the interval quickly and try these questions. Okay. Try these questions. So interval until how maybe 10, 15 or yeah, I'll give you 15 minutes. The time is try these questions. Okay, next, try these questions. You can find these questions in the Tute. So the time is 10. Time is 10 for 2. I will give you interval until 10. If it takes 15 minutes, 17. I'm gonna start exactly on this time, okay? But if you like, quickly take a 5-minute break and start doing these questions, okay? Quickly take a 5-minute break and start doing these questions. But if you need a rest, because we have to go until 12. So, but if you feel like you need a proper rest, then don't do any questions. Take a 15 minutes break, walk around, okay, do some exercises, then return to the session. Okay, let's wait for like 1 or 2 minutes until everyone joins. Others, start doing the questions. Start doing the questions in the electromagnetic tube. These are the type of questions that you can get. Quickly do the questions. And you can hear me clearly, right? Can someone please respond? Nice. Try these questions in last tube, last page of your tube, electromagnetic tube. You have question number 1, 2, 3, and yeah, that's all. Quickly try these questions. We'll take only like few minutes for all these questions. Then we'll move to current electricity and maybe geometric optics, like things like that. And after today's session, what will be remaining most probably is electronics. The from the things that you mentioned that is difficult, what would be remaining will be electronics. I can do a separate session for electronics, but do you get enough questions from electronics for levels? Would you find it beneficial? Please respond. An electronic session, would you find it beneficial? You get questions from enough questions from that part. That's the issue that I have. Okay, you sometimes get. YouTube live students, you can also mention. Okay, there's a prediction that you can get a main question from electronics this time. Okay, okay. Okay, then let's do a proper electronic session then. A separate electronic session, separate to do electronics only because I think many students find electronics part hard, right? I think almost all the students have find electronics part hard, right? Am I correct? So if that is the case, what we can do is maybe next Tuesday morning, something like that. Is it too close to your levels? Maybe next Tuesday morning, I will do all the electronics. I will cover the whole electronic lesson. What about that idea? Okay, then let's assume I'll confirm in the group, okay? But please fill that Google form so that I can get a good idea. But most probably I will confirm in the group, but most probably it will be next Tuesday or something like that. Next Tuesday, it will take like 2, 3 hours for me to discuss everything about electronics. Let's do it that way. Okay, then I'll start discussing the questions. Uh, let's start from the first question. Let's start from the first question. The following diagram indicates a movable conductor AB which is placed in a magnetic field. If the switch is turned on, in which direction will the AB conductor move? Okay, this is the diagram that I have to work with. Battery is in this direction. Battery is in this direction. So it will create a current in this direction. Battery is in this direction, so it will create a current in this direction. This is the north and this is the south. So there will be a magnetic field in this direction. So what is the law first? Can someone mention what is the law that we have to use? Which hand? Which hand law? What should we use? Ah, nice. Fleming's left hand rule. Fleming's left hand rule. So current will be moving in this direction. Current moves in this direction. Magnetic field north to south. Current this direction. Magnetic field north to south. Then force in this direction. Out towards, away from the board. Away from the board. Force is away from the board. So I think vertically upwards to the plane. Vertically upwards to the plane. Away from the plane. Away from the plane. Is that clear, everyone? Is that clear? That's how you apply Fleming's left hand rule. Then question 2. Following is a diagram drawn to explain the action of a transformer. M1 and M2 are insulated copper coils used for this. Names state whether there is a deflection in the galvanometer in the following instances. Now we know this. When closing the switch, yes. When the switch is kept closed, no. When opening the switch, yes. We know that, right? We just did some question. Did an exercise related to that. Out of M1 and M2 insulated copper coils, which coils are used as primary and secondary? Okay, we know that primary is where we provide a current. Secondary is where the current is induced. So this is where we provide a current. We use a battery and we provide the current. We do the changes to this system. We do the changes to this system. So this is the primary. This is the primary. And due to those changes, it induces a current here. Then this is secondary. This is secondary. M1 is primary, M2 is secondary. Write two changes that should be done in the system to get a higher reading in the galvanometer. Okay, nice question. Okay. If you need a higher reading in the galvanometer, what should you do? If you need a higher reading in the galvanometer, higher reading in the galvanometer means higher change, higher change. One thing you can do here is, as we know, when you increase the number of loops in the secondary, can you remember? When you increase the number of loops in the secondary, it will create a higher voltage. Can you remember? But creating higher voltage, is it okay? Or else, let's go with some simple answers first. You can increase the value of this battery. Can you remember the equation? Okay, I'll explain it properly. Can you remember the equations? V primary over V secondary equals N primary over N secondary. And V primary into I primary equals V secondary into I secondary. These are the rules related to the transformers. So what we can do is, now the target is to increase V secondary. Increase V secondary. Or else to get a higher current. To get a higher current through the galvanometer. That is the target. To get a higher current through the galvanometer. So one thing that we can do here is, if we want, we can increase the voltage of this battery. When you increase the voltage of this battery, when this change happens, it will create a higher current. When it creates a higher current in the primary, it will increase the value of this side. Then eventually this side will also improve. Eventually this side will also improve. Clear? So higher the current, okay? Higher the current in the primary, higher the current in the secondary. So you can increase the value of this battery. Okay, you can increase the value of this battery to get a higher reading in the galvanometer. Or you can change the number of loops here. You can adjust the number of loops here. Then you can increase the reading in the galvanometer. Another solution, you can adjust the number of loops in primary and secondary to get a higher current through the galvanometer. Here you can provide a higher power to the primary by increasing this battery power or by increasing this voltage. It will deliver a higher current or a higher power to the primary. Eventually, it will increase the current in the secondary. So it will create a high value in the galvanometer here. Or else what you can do is you can increase the voltage of the second. You can adjust the number of loops in the primary and secondary such that, based on this equation, such that it increases the current through the galvanometer. You have these solutions here. Then next one, write two changes that should be done. Okay, next one. But write the relationship between the number of turns in M1 and M2 coils if the transformer to use as a step down or step up. Okay, we know that, right? We know that in a step down transformer, step down transformer, primary has higher number of coils. For a step down, N primary is larger than N secondary. Can you remember? For a step up, N secondary is larger than N primary. So for a step down, N secondary is lowest. For a step up, N primary is lower. Okay. Next one. Write an instance of using step down transformers in day-to-day life. Can you mention someone? An instance where we use a step down transformer. Can someone please mention quickly? Instances where we use step down transformers in real life. Anyone? These are possible questions in exams, okay? Anyone? Others? Yeah, it's good. One thing would be in our distribution lines. We get very high voltage values in our distribution lines, and before delivering them to our houses, before delivering these current to our houses, they step down. They reduce the voltage to sometimes 10,000s of voltage they reduce to 230 volt. So they step down to 230 volt before delivering current into our house. Even after that, we get 230, but my laptop, maybe my mobile phone needs only 12 volts. In our grid, I get 230 volts, but my mobile phone, to charge my mobile phone, what I need is only 12 volts. So when we connect our sockets to the plug point, there's a step up, step down again. We reduce to 30 volt to 12 volt. We get to 30 volt and reduce it to 12 volt. That's a step down. That's a step down. Clear? That's a step down transform. Clear? So when delivering from distribution lines to our houses or when getting power out from our socket, we use step down. We need this example, but we quickly answer the questions. What is the direction in which the current should flow through the wire to form the magnetic field as shown in the figure? Here, To create a magnetic field like this, we have to use right hand rule, not Maxwell's right hand rule, as I remember. If thumb is moving in this direction, then there will be a magnetic field in this direction. See, so the current should go upwards. Which rule do you use to determine the direction of the current in figure 1? As I remember, it was Maxwell's corkscrew law or else right hand rule, right? Right hand rule. Can you remember the name of the law? Right hand grip rule. It's right hand grip rule or Maxwell corkscrew law. Next, in figure 2, what is the direction of current flow when the switch is closed? We did this. Current will go in this direction, in this direction. What is the direction of the movement of AB rod based on X and Y? We know that. We explained that before. Rod will move in this direction. Can you remember? It will move in this direction. Write down the two strategies that can be used to increase the speed of the motion of AB. Nice question. If I need to increase the speed of AB, what should I do? Here, what is the reason for this motion? It's the current and the magnetic field. Clear? It's the current and the magnetic field. Due to the current and the magnetic field, it creates a force on this thing. So to increase, definitely you have to increase the current or you have to increase the magnetic field. So the two solutions would be you can increase this battery value. You can increase this battery value. Okay. You can increase the value of this battery. It will create a higher current, then it will create the force, increase the force. Or you can use a stronger magnet. Okay. You can use a strong magnet for this. It will again create a very high force. Clear? It will again provide you a very high force. Clear? Okay. Question 4. The diagram shows how both primary and secondary are located in a transformer. What type of transformer is shown in figure? Now you should see here you have more rounds in the primary. Then what is the name of this one? What is this one? More windings in primary. It's a step down transformer. Here, more windings in secondary. It's a step up transformer. I mean, sometimes you may feel that these things are useless. What is the use case of this thing? Okay. What is the use case of this thing? I mean, in O levels, you won't see what is the use case of the things that you are learning. In A levels, you will see them to a certain amount. Then after, I mean, when you are in the university, you will see, oh, okay, we learned all these things for this. I mean, I learned these things in O levels. I did some more electronics and electromagnetics in A levels. But now we develop transformers. I mean, like 6 months before, we developed a set of transformers to a company for a satellite. So when we are developing transformers for a satellite, I mean all these small theory parts together, when we know all these things, it creates a perfect transformer suitable for a satellite. So there are things like that. So only you will just have to learn now, learn the basic concepts, understand things properly. The use case will be huge. Use case will be huge one day. Okay. But first of all, before that, you have to be, I mean, learn the fundamentals like this. That is the basic idea. So next one, if the number of turns in the primary coil and the secondary coil of that transformer are 100 and 1000 respectively, find the output voltage at the end of CD. Okay. Now, if the number of turns in the primary coil and the secondary coil of the transformers are 100 and 1000. We provide 230 volt here. So what is the equation? V primary over V secondary equals N primary over N secondary. What is the primary voltage? 230. Secondary voltage, I don't know. In primary, it's 100 and 1000. I think it's small printing mistake, right? Here, this should be 1000, this should be 100, right? So, in primary should be 1000 according to this image. In primary should be 1000 because there are more rounds in the primary. In secondary should be 100. So, I can solve this. V secondary equals V secondary equals 23 volts here. V secondary equals 23 volts. Is that clear, everyone? Is that clear, everyone? Nice. Next one, we use we write use of transformer shown in figure 2. Write the use of the transformer used in figure 2. Figure 2 is a step up transformer. Give me some examples for the use cases of a step up transformer. Tell me the usage of a step up transformer. Can someone quickly tell me the usage of a step up transformer? Use case of a step up transformer. Quickly. YouTube live students and Zoom students, quickly. Use case of a step up transform. I got one answer only. Others. Use case of step up transformers. Yes. When in our power stations, so what actually happens is in our power stations, our turbines, maybe not actually, our turbines create a certain voltage. We use step up. We use step up and increase this voltage to a very high value and we send them through the distribution lines. When we send them through the distribution lines. Why do we use a very high voltage in distribution lines? To save power. When we increase the power, when we increase the voltage a lot, when it goes to wires, the power loss is reduced. So to save some power, we increase the voltage to very high values and send them to distribution lines. So this is a use case of a step-up transformer. Now, you can't give 10,000 volts to your house, okay? Everyone will die. So before giving it to your house, we step down it. And we deliver it to your house. Is that clear? That's how the current moves in our grid. Clear? That's how the current moves in our grid. And I got more answers. Maybe microwaves, yes. Sometimes we increase the voltage to very high values in microwave ovens such that we can get a good power. So these are good examples. So especially in our power stations, we use step up. In our power stations, we use step up transformers. And at the same time, there was a question like this. Some students asked this question from me. How can we a proper plan to, improve your MCQs? A proper plan. Whenever for all the MCQs, not only for science, for all the MCQs, for me, when I'm doing MCQ, what I usually do is I have my own set of symbols, okay? I have my own set of symbols. That means it's something like this. Whenever I'm doing a MCQ, okay? Whenever I'm doing a MCQ, okay, I'll give you a maybe, anyways, let's do it this way. Assume that you have a, I'll start like this. This is just a set of techniques, I mean, that I use when I'm doing MCQs. First of all, I usually have a set of symbols. That means I'm not going to do all the MCQs. Some MCQs are difficult, some MCQs are difficult to understand. So I categorize MCQs first. That means whenever I'm doing a question, if it is easy, if I get the answer, if I know the answer, or if I can get the answer, I quickly do some calculations and get the answer. There are certain MCQs that I can use a short method or get a workaround and quickly go for an answer, but I'm not that sure about that one. So maybe second one, no issue. In the third one, I'm not that sure about the question. I just go get an answer, but I put a symbol like this next to the question number. Maybe a line. Then for okay, fifth one, I have no idea. This is I have an idea, but here I have no idea. I don't know anything. I put a cross here. I wasn't able to get an answer for this. And I keep doing like this. Then soon after finishing the MCQ, okay, I quickly leave these kind of questions. Otherwise, if I stay in this question for a long period of time, trying to do this question will eventually reduce my time and I won't be able to maybe read final questions. Okay. So I quickly pass these questions, but I put a symbol like this and I quickly try to finish the whole paper as soon as possible. Then after finishing the paper, I first return to this process. Why? I mean, I don't have enough time to go through the pages and look into the questions that I didn't do. It's easy when you have a symbol like this. I first go to this process. Then I try to figure out this process. Then I get answers for this process. Then after finishing this process, if I have time left, I try these lines. I check them. I check for the answer. I try to verify. That way I can skip the difficult questions, skip the unsure questions, and I can quickly go through as soon as possible. Clear? I can quickly move through the question quickly as soon as possible. It will save some time. Clear? It will save some time. Then later, using that time, I can do these questions and these questions. And another thing is, I sometimes in my MCQs, when I'm doing MCQs, I maintain a table. I maintain a table like this. How many MCQs do you have for one MCQ? How many choices do you have? How many choices do you have for MCQ for? Okay, one, two, three, four. I take a rough sheet and create a table like this. It will take like 2 seconds to create this table, right? Now in the fifth question, I'm not sure about the fifth question. I have no idea how to get the answer for fifth. I have no idea. So when I face an issue like that, what I can do is for question number 5, what can I do is I can quickly, when I read the question, there are certain answers that I know for sure they are not the answer. That means maybe in question 5, I don't know the answer, but I'm sure that 1 and 2 can't be the answer. I'm sure about that. So when you have this kind of a certainty about at least 1 or 2 answers, then question number 5, it can't be 1 or 2. Why? When I mark it like this, only for the questions that I'm not sure and the questions that I didn't answer. Assume that you have your last 5 seconds and the invigilator is coming to collect your paper. You have only 5 seconds. When you come to this question, you don't have enough time to read the question again. understand the question again. You don't have time for anything. But you can quickly look into a table and you can see initially when I was reading the question, I said that these two can't be, then I can choose one of these two questions. See, there's a high probability that you get the correct answer here. There's a 50% probability. Otherwise, when you have 5 seconds left, you will somehow choose one or two or three or four. Then you have a high probability to get that wrong. Clear? Clear? So, and there are some students, they mentioned they usually don't get enough marks. So, A-level MCQs, usually the reason behind the losing marks for MCQs is not having a proper plan. Definitely in a 40 MCQ paper, you have around 25 questions that you can easily do. But what happens is there are like 15 questions which are difficult. Due to those 15 difficult questions, you lose time that can be used to answer those easy 25. Clear? So first of all, you have to find the easy questions. You have to forget the difficult questions. You can put process in difficult questions and you first finish the easy set. Then you finish the difficult set. Then you finish the uncertain set. You must need a very nice plan like this. So if you have a very nice plan like this, it's really easy to get marks in the MCQ paper. Clear? It's really easy to get marks in the paper. Everyone got the idea? So what you need is not the knowledge. What you need is the plan. In life, for many things, people think that I don't have enough brain capacity to do this thing. I don't have enough time to do this. I don't have enough money to do this. But basically, in many things, what you don't have is a plan. Okay, you don't. I mean, you have more than enough time. If you can create a timetable tonight for tomorrow, if you follow this plan, you will see you have a lot of time. But what you don't have is a timetable or a plan. Okay, you may lose a lot of marks in MCQs, not because you have less knowledge. Yes, sometimes if you haven't worked yet, work properly, you may have a less amount of knowledge. But the main reason is you don't have a plan. So what you need is a very nice plan like this, very nice prototype like this, where you are gonna follow. Okay, okay. You need a very nice plan like this, and for everything, create small plans like this. Okay. And for some students, they tend to get a lot of careless mistakes. Okay. So if you do a lot of careless mistakes in paper, who are the students who always get uh, MCQs wrong because due as a reason of not reading the MCQ properly, not reading up to the last word. Maybe sometimes they ask the possible answers, sometimes they ask the answers which are not possible. When you are in a hurry, you don't understand, you don't read whether it's possible or not. So for me, I had the same issue. What I did was you can't think that you are not going to do careless mistakes. Some students, what they do is they think that I'm not going to do any careless mistakes next time, but it never happens. Right? Again, you need a plan. Just telling to yourself that you are not going to do careless mistakes next time, it's not going to help. So the plan should be, from my point of view, the plan should be, what I do is maybe in every question there's a full stop, right? I usually after reading every question, I cut this full stop. In certain scenarios, sometimes I read up to this point and quickly get an answer and move. But after the paper, when I go through the paper, I see what are the questions that I haven't cut this full stop, that I haven't put a mark on this full stop. Then I know I haven't put a mark on the full stop because I haven't read it up to the end because we don't do that purposefully, right? We forget to read the last part. But when you have a habit like this, you can again go through the paper and see what are the questions that I haven't read until the end. Then I read them properly again. Then I come to full stop. Then I check whether I have got the correct answer or not. See, use physical methods like this. Okay, you understood that? You understood that? And improve the patterns you are writing things. Make things tidy. That means if you write 4x plus 5 minus x squared equals 0. If you write like this, there's a high tendency that you forget this part. The reason for that, to get rid of that, if you have to write something like this, put equal 0 here, put equal 0 here. Clear? In certain questions, if you usually forget minus mark, if you know that it is a common habit in your life, put a star there. Then after, when you are rechecking the paper, you see the star. When you see the star, okay, you can check again whether you got it correct or not. See, use physical methods like this. Use physical implementations get rid of all the errors that you can make. Clear? Plan stuff, okay? Plan things, then you can get a lot of marks. Everyone, is that clear? YouTube students and Zoom students? Nice, nice. And do you have any single medium friends who request for single medium seminars too? Anyone? Just let me know if there's a requirement like that. Do you have any single medium students who request for single medium seminars too? But I think for single medium students, they have a lot of seminars, right? I mean, in A levels, for A levels, I do both single medium classes and English medium classes. So I'm capable of teaching both in English medium and single medium. But I decided to do English medium seminar only because I think single medium students have a lot of seminars, right? Going on. But English medium students, they have, I mean, very low amount of seminars, right? Which I feel unfair. That's why I decided to do some seminars for you guys. And and everyone, like, if possible, try to do A levels in English medium, okay? Why I even suggest this for single medium students and Tamil medium students too, because I mean, anyways, after the school, you have to anyways learn in English. So it make your university life really easy. Up to this point, like up until recent, the problem in the English medium industry was there were no classes, good classes. But now you have online classes. We started teaching as engineers. We started teaching, so a lot of new people came to the industry to teach. Now there's no such issue with the English medium science, English medium physics in A levels. So try to do English medium if possible. And if you have friends who needs English medium seminars too, let me know. I can try to do something, but mainly what I was trying to do is I was trying to fill this gap where single medium students get a lot of seminars and English medium students have none. I needed just to fill that. I needed to fill that gap. So do you know anyone doing Tamil medium? Not exactly, but if you need, I can try to find someone for you. Yes, we have a lot of students in University of Morato, my colleagues. Okay, so what else? What else? What are the things that you need to discuss quickly? Current electricity or optics? Let me know quickly. I can go through the current electricity lesson within 10 minutes. Do you need that? Anyone? What do you need me to discuss? Okay, then we'll see optics. And for electronics, not today. I'll do electronics separate because it's a huge lesson. So I'll try to do that. Okay, so then let's do optics. Since everyone's requesting, let's do optics. Yeah, there are requests for electronics. Yes, I will do it separately. We need like 3 hours total. So there will be a separate session for electronics only. I'll do it that way. So geometric optics, we call this a convergent light beam. A light beam which tries to get together, we call it a convergent. And this is divergent and this is parallel. So talking about the reflection, what is the laws? What is the how many laws are there for reflection? What are the laws of reflection? Quickly mention. What are the laws of reflection? What are the laws of reflection? Paravartana niyam. Yeah. What are the laws of reflection? This I and this R is equal. Incident angle is equal to the reflection angle. I is equal to R and they are on the same plane. They are on the same plane. You can't have I in this plane and R going in this plane. No. Okay, they should be in the same plane. They must be in the same plane and these angles must be equal. I and R must be equal and they should be in the same plane. Okay. So based on that, we can find where the image of a mirror is formed. We can find where the image of a mirror is formed. How? See, I have O here. This is my object. I have O here. This is my object. And here, then this is I. This is I. Then this is R. Since I is equal to R, it will move like this. Then here another ray. This is I. This is R. So since I is equal to R, it will move like this. Again, this one, it moves like this and returns like this. Now you can see my eye here. You can see my eye here. My eye sees these two lines. My eye sees these two lines. So my eye think that these lines comes from a point here. I mean, my eyes don't know physics, okay? My eyes don't know physics. So they don't know that there are something like this, they reflect, they come. Your eye have no idea about physics and what is happening. Your eye thinks that these rays are coming from a point at this point. So your eyes see that there's an image here. That image is not actually there. Object is here and these are reflected rays. So what is happening is reflection. But my eye doesn't have a separate brain to think for himself. So my brain have no idea. My brain thinks that, okay. So my brain thinks that these rays comes from a point at this point here. That's what my brain thinks. Okay. That's what my brain thinks. That's why the image is formed here. Clear? Did you understand? Please respond. That's how the image is formed here. Did you understand? So since these triangles are similar, this triangle, Since this triangle and this triangle are similar, this distance and this distance is equal. So this from the mirror distance to the object is equal to the distance to the image. Clear? So the next part, curved mirrors, and there's a set of rules related to curved mirrors, right? I'll show you a video so that it's easy to understand. So when you talk about curved mirrors, we have concave mirrors and convex mirrors, right? We have concave mirrors and convex mirrors. So what are the rules? What are the rules? There's something called focal point. If you send some rays, parallel rays, if you send some parallel rays, all these rays to a concave mirror, all these rays goes through the same point. All these rays goes through the same point. This point we call that the focal point. Clear? This point we call it the focal point. Clear? That's the focal point. Then for a convex mirror, when you send rays parallel to the principal axis, they moves like this, they reflects like this. But all these rays looks like they are coming from a point in this side. It looks like they are coming from a point in this side, and this side we call this focal point. Clear? Focal point. And when we are working with maybe concave mirrors, we have to, I will show a video and explain everything. I'm just going through the theory points. Then I will show a video and explain. If these rays comes through the principal axis, it will return through the principal axis. If they come like this, they will reflect such that it obeys reflection laws. That means I equals R. I equals R. Then if these rays comes parallel to the principal axis, they will go through the focal point. They will go through the focal point. Here also, if they come through the focal point, they will return parallel to the principal axis. These are the rules. If they come to the optic center, if they come through the center of curvature, they will return through the center of curvature. Who made these rules? I mean, these are not magic or something like this. That's how actually the mirror behaves, okay? According to reflection laws, that's how the mirror behaves. You can understand it by this video. Uh, this is an actual mirror, okay? This is an actual mirror and a laser. This is an actual mirror and a laser. So, we just send a laser ray. See what happens. When you send parallelly, when you send parallel rays, what happens? See, it goes through focal point. That's how actually it behaves. That's how it actually behaves in light. When it goes through the focal point, it returns parallel. See, when it goes through the focal point, it returns parallel. When you send it through the center of curvature, it returns to the center of curvature. When you send it like this, it will return like this such that I equals R. See? So it's not magic or anything like that. That's how actually, okay? That's how actually the concave mirrors behave, okay? Reason is simple, okay? Reason is simple. Only reason is, only reason for this behavior is reflection law. That means this is your center of curvature. So you have something like this. Now you send something parallel. This angle is I. It reflects. It reflects such that I equals R. It reflects such that I equals R. Ah. Now I send another ray. This is the center of curvature. It reflects such that I equals R. Then this point we give it a name called the focal point. See, what actually happens is nothing special or nothing special to concave mirrors, convex mirrors. It's nothing special to these things. They are just following the reflection laws. Clear? They are just following the reflection laws. That's why, that's why when you send something to the center of curvature, this is the center of curvature. C. That means this is perpendicular. When you send a ray through the center of curvature like this, then the angle is zero. Angle is zero. So it will return with the angle of zero. That's why it comes like this. Is that clear? Everyone just mention in the Zoom chat and the YouTube live chat. What actually happens is not anything magical or anything related, special related to optics. What actually happens is just they are following laws of physics, laws of reflection. Clear? Okay. Now, based on these rules, I can find where the image is formed. If I keep an object like this, I can draw two lines to figure out where the image is formed. See, I can draw a parallel line like this. A parallel line will go through the focal point. A parallel line will go through the focal point. So it comes like this and it goes like this to the focal point until my eyes. Then, if this is the center of curvature, if I draw something like this through the center of curvature, it will return through the center of curvature. It will reflect and return to the center of curvature. So as a result, my eyes will see these two rays. Then again, my eyes, uh, so then my eyes have no idea about physics. My eyes thinks that these rays are actually coming from an object. So it trace back and check whether where can I find these rays. It sees that these rays get together at a point like this. Then my eyes think that there's a object here. That's the image seen by me. Clear? That's the image seen by me. So what actually happens is my eyes sees an illusion. These things are reflected. My eyes don't know about physics. It thinks that these rays are coming from a point here. So my eyes think that image is formed here. Then if I keep it at the focal point, they will go to infinity. They will meet at infinity. If I keep it between the focal point and the center of curvature, between the focal point and center of curvature, your image will form here. I will draw one thing and explain you it properly so that you can understand. You have the mirror like this. Now you have the focal point here, center of curvature here. Now you have the object here. And you have your mirror like this. So I can draw, there are millions or billions of light going out from this pin, okay? There are millions or billions or trillions of light streams, light rays going through this point. But to get my image, what I need to do is I have to draw only two lines. I know that if there's a ray going parallelly like this, if there's a ray going parallelly like this, I know that it returns, it goes through the focal point. If any ray goes parallelly like this, it returns through the focal point. Clear? Then, if a ray goes through the center of curvature, if a ray goes through the center of curvature, it returns through the center of curvature. It returns through the center of curvature. Now these rays get together at this point. These rays get together at this point. So I can see, an image formed here. I can see an image formed here like this. Here. So what happens is if I actually keep a paper here, if I actually keep a piece of paper here, these rays will get together. These rays will get together and create this image on this paper. Clear? If I actually keep a piece of paper here, these rays will get together and create an image here. Okay? They will get together and create an image here. So, what is important here is if we can take this image to a paper, okay? If we can take this image to a paper, what do we call that image? Can you remember? If we can take this image to a paper, piece of paper, what can we call that image? Everyone, try to give an answer. Nice, nice. If we can get something to a paper, piece of paper, we call it a real image. Real image. Why? These rays actually get together at this point. So it actually creates an image. So you can keep a piece of paper and see that the image formed here. But in this scenario, in this scenario, this is not an actual image. Why? These rays come to my eyes and my eyes think that it's coming from a point here. But it's actually not there, right? It's actually not there. It's just an illusion seen by my eyes. So these kind of things, which are not made of real lines, but it just seems like that. It just seems like that, then we call them a real virtual image. Clear? We call them a virtual image. That is the idea. So I think you can see Here, I think you have done that. Okay, I'm showing these things because it's good to have a very good practical idea. There's practical questions, sometimes mathematical questions. So it's good to have a practical idea and it's good to see things from your eyes. I mean, then it's really easy to understand. So real image is like this. See, you can actually take it to a piece of paper. See, now what happens is there are rays coming from this side and they get together here. This is a lens, okay? This is not a mirror, this is a lens. See, you have lens in your syllabus, right? See, rays actually get together and form the image. See, that's what we call a real image. That's what we call a real image. See, image is formed in the piece of paper, but sometimes, see, image actually forms in a piece of paper. This is a mirror, I think. See, rays come like this and return like this, and they get together and create an actual image. This is real images. But sometimes you only see stuff. See, sometimes you only see stuff. See, now you see the car through this one, but it's not actually there. It's not actually there. Your eyes think that the car is here. Okay, see, you can see the car. You can see the car through this lens. So your eyes think that the cars are in the lens, but actually car is here. So these kind of thing we call them virtual images. We call it virtual images. Is that clear, everyone? So likewise, you can keep drawing diagrams like this and figure out where the image is formed. Okay. You only have to draw the basic required lines. Only two lines. Two basic lines so that you can figure out where the image is formed. Just remember this thing, okay? Who creates an virtual image? Who creates a real image? What are the upright images? What are the inverted images? You can see in the first one, it's an upright image. In the first one, it's an upright image. But all other are upside down. See, upside down image, upside down image, upside down image. It's better to remember these things and just learn how I taught you to draw these diagrams, okay? Knowing that would be enough, okay? Learn how to draw this diagram properly and it would be enough. Here, next one, reflection from a convex mirror. Again, same rules apply here, same rules. If something goes to the principal axis, it returns to the principal axis. If something goes towards this focal point, they returns parallelly. If something goes parallelly, it returns like they are coming from the focal point. If something goes towards the center of curvature, they return such that they are coming from the center of curvature. Is that clear? Very basic rules. Very basic rules. Clear, everyone? This set of rules it's better to remember. Just mention in the chat. Clear, everyone? Nice, nice. Thank you. So, how the image is formed with a convex mirror. Let's see. I'll draw one diagram. Then you can easily understand. Just follow the rules, okay? Just follow the rules. Here you have your concave mirror. Sorry, convex mirror. This is your principal axis. Here you have the focal point. Here you have the center of curvature. Okay. Here you have the object. You keep an object like this. Now there are millions or billions or trillions of light rays going out from this object. But what is required is to find the draw the most appropriate ones. So I will draw the most appropriate rays. What are the most appropriate rays? If something goes parallelly, if something goes parallelly, they reflects such that they reflects and they looks like they are coming from the focal point. It's a basic rule. So this ray will go like this. And here also it's not magic, okay? They are just following reflection laws. If something goes like this, they returns like this. Then if something goes like they are moving towards the center of curvature. If something goes like they are moving towards the center of curvature, they reflects in the same path. They reflects in the same path. Whatever goes towards the center of curvature returns like they are coming from the center of curvature. Now I have my eyes here. I have my eyes here. My eyes sees these two rays. And again, my eyes doesn't have any brain. He thinks that this line and this line gets together at this point. So my brain, my eyes think that they are coming from a something here. But there's nothing here. It's just a virtual image. An illusion seen by my eyes. Clear? It's just an illusion seen by my eyes. There's nothing here. But my eyes think that these rays are coming from this point. Clear? That's how this thing works. Okay, that's the concept of real and virtual images, real and virtual objects. Clear? One thing is an illusion seen by my eyes, other thing is an actual image. Is that clear? Just respond. And I remind everyone, just fill the Google form so that and ask others too, so that I can have a very good idea about what to do in the next sessions. So there's a certain certainty that you can get a question for electronics this time, right? There's some kind of certainty, right? If that is the case, yes, it's better to do electronics too. I'll try to do it for both English and single medium students if there's that kind of issue. We'll see. Okay. So next part. And I mean, it's these days use a proper plan. I mean, I think most of your O-level classes also you may have given like you may short notes. I mean, even now in our A-level classes we give short notes. We do revision sessions. We do paper classes from the beginning. Every week we write a paper. There's a lot of plans going in our A-level classes too. So I think same plans must be going through nowadays in O-level classes, right? When we were doing A-levels, there was nothing like that. But now we do that for our students. So I think same should be happening in O levels. I have no idea about O level classes, but I think same scenario may be happening there, right? So just go through these notes, okay? Get the short note tunes if they are available from your classes. If your class is, if they are not giving anything like that, ask it from your friend. Get a note like that. There may be papers released from different classes. Collect them. Ask from your friend for those papers and try them. Check with the marking schemes. Go through that process. Okay, share with others. Share with your friends. Okay, then they will give you back. So this is not a competition or a war. Okay, this is not anything like a competition or a war. Just share everything that you have. Okay, all the notes, all the tunes, short notes given by your class, short notes given by your school, school papers, class papers, model papers, share everything and work together to get a good mark at all levels. Okay, that is the main target. At the end of the day, everyone's going to do A levels, right? Which question? Which question? Can you please mention? A student has mentioned that he has a question. Can you please mention that? Until he mentions, I'll continue. So refraction. What? How many rules are there for refraction? Vivartaneta නීති කීයක් තියෙනවද? Again, two rules: Snell law and the first law. What is the first law? All these rays, incident ray, and this one, this perpendicular line, and this ray, refracted ray. All these rays are in the same plane. All these rays are in the same plane. Clear? And what is the second rule? We call it the Snell law. We introduce something called index of refraction. Vartananke, we call it refractive index or the index of refraction. It is equal to sin I over sin r. What is sin I over sin r? That means sin I this is the incident angle. We take the sine value of I. This is the refracted angle r. We take sin I over sin r. It is equal to the index of refraction. So there, someone has mentioned a question like this. Height of an object is 3 centimeters and it is placed 4 centimeters in front of the concave mirror. If the focal length is 6 centimeters, find the position, size and the nature of the image. Okay, it's a good question, but you don't have anything called mirror formulas, right, in your syllabus? Can someone please mention? I'm talking about the question asked by that student. You don't have anything called mirror formulas, right? So I think this question is too much for your O levels, because to get the answer easily for that one, okay, to get a quick answer, you need mirror formulas. You have mirror formulas and lens formulas. In A levels, you have lens formulas. So without mirror formulas, this will be a little bit difficult to get an answer for this, okay? That is the issue here, okay? You need to learn mirror formulas to get an answer. But I'll try to explain you that a little bit. Height of an object is 3 centimeters. Okay. We'll see. Wait, I'll try whether it's possible to explain it to you guys. They're asking the exact size, right? And exact position, right? To get the exact size and position. No, I don't think. Height of an object is 3 centimeters and it is placed 40 centimeters in front of a concave mirror. If the focal length is 6 centimeters, find the position. Yeah. I know how to get the answer for that question, okay? And you also can go and search in the internet. Just search on the internet, you will see something called mirror formulas. You have 1 over v minus 1 over u equals 1 over f, 1 over v plus 1 over u equals 1 over f. But I think it's not available in your syllabus. I think They can't ask a question like that. But definitely, if it is possible, I'll do in the next session. But I'll first have to confirm with the all-level teacher because I'm an advanced level teacher. So I know these things, but me knowing things doesn't mean that you have to know that because still you are in O levels, so I can't teach you too much things not related to O levels because it's really close to O levels. So I'll check and let you know, okay? But you can just okay. The position they are not asking you to calculate. They are not asking you to calculate. They are just asking you to give a brief idea of the image. Then it's possible. It's possible. Then let's do that. I'll explain that. So the question given by the student is like this. There's an object, okay? There's an object. There's a mirror, a concave mirror. Focal length is 6 centimeters, okay? Focal length is 6 centimeters. Attention. Focal length is 6 centimeters. And it is placed 4 centimeters away. That means it's here. It's inside the focal length. And its height is 3 centimeters. They are asking the position of the image, size of the image, nature of the image. So you should see the easiest way is first categorize, find the category of your image. In your textbook, from your textbook, you know that if you place something inside the focal length, this will be the diagram. Clear? This will be the diagram. If you place something inside the focal length, this will be the diagram. Then you will get a virtual image, a larger image, and placed in this side of the mirror. Is that clear? Is that clear? Did you get the answer? Larger than object and virtual. So if that's all, yes, it's possible. You can get such a question in O levels. But if they actually ask this distance, is it 12 centimeters or 8 centimeters? If they actually ask this distance, then no. For that, you have to learn formulas. So if you get a question like that, what you have to do is first try to find the category. Focal length, you know, distance, you know. Then you can find whether it's inside the focal length or whether it's on the focal point or whether it's in between the focal point and the center of curvature or whether it's on the center of curvature. Then based on that, you can directly get an answer. Okay. So these things you have to remember. Okay. But so you have what you have to understand is you have to understand the position of the object uh, relative to the position of the focal length. If you know these two, then you have the answer here. If you know the distance to the object and if you know the distance to the focal point, then you have the answer. Okay. So next concept, we learned Snell law. We learned Snell law. Then we learned something called the critical angle and the total internal reflection. What happens here is according to Snell law, okay, according to Snell law, higher the I, higher the R. Higher the I, higher the R. So you keep increasing I and it keeps going like this. And at some point, when you increase I to a certain level, it goes through this surface. It goes through this surface. Clear? You keep increasing I, then R keeps increasing. And when I reaches a certain value, okay, when I reaches a certain value, it goes through this surface. Clear? That situation, okay, that situation we call that the critical angle. We call that the critical angle. And if you exceed that angle, refraction will stop and it will start reflecting. If you exceed the critical angle, refraction will stop and it will start reflecting internally. We call that total internal reflection, Purnabhyantara Paravartane. Is that clear? This is what we call the critical angle and the total internal reflection. In your fiber optics, now a popular topic, fiber optics, what happens is total internal reflection. Purnabhyantara Paravartane fiber optic. What happens in a fiber optic cable? What happens in a fiber optic cable? Fiber optic carries messages or data as optic signals. Rays go like this, reflect like this, then reflect like this. They keep reflecting. So this is very efficient than sending signals using current. Initially, at first, the signals were going you through current pulses, but it consumes a lot of energy. When signals go as current pulses, it consumes a lot of energy. But now, when signals go like optic rays using total internal reflection, they reflect internally. When they move using total internal reflection, it saves a lot of power. So one of the main use cases of total internal reflection, Purnabhyantara Paravartane Pradhanam Prayojana. One of the main uses of total internal reflection is fiber optic cables. And have you seen in cartoons, you see something like this? In submarines. In submarines. In submarines, you see they look from this point. And there's something going like this. How they look for Roman ships and stuff. There's a person looking from this point, and you see ships from this point. How can you look from here and see it here? How's that possible? How's that possible? Have you seen this thing in cartoons? Have you seen this? Okay, it's either a mirror or a prism which uses total internal reflection. That means it may be a mirror or something like this. Something like this. A prism like this. So light rays come like this. There's a ship here. Light rays come to the mirror, come to this surface like this. They here they experience total internal reflection. Then here also they experience total internal reflection and it comes to your eyes. Clear? That's how they comes to your eyes. Clear? Through total internal reflection. Purna Abhyantara Paravartane Haratama Egola Hade. Clear? And endoscope, fiber optic cable, this submarine thing, all these are use cases of total internal reflection. Purna Abhyantara Paravartane Prayojan. Clear? Now, then one of the main use cases of total internal of refraction. Varatane Pradhanam use case. Okay. Varatane Pradhanam use case. One of the main use cases of refraction is lenses. See, I'm wearing a lens. I think most of you guys are wearing lens. We have telescope, microscope, all these things are made out of lens. Your mobile phone camera made out of a lens. So lens is one of the most important things today. So it is a result of refraction. Why? Light rays refract through these lenses, then they create certain shapes. That's the use case of a lens. So again, you have to follow several rules, okay? You have to follow several rules when you are drawing ray diagrams to an object. Okay, what are the rules? If If a ray is parallel to the principal axis, it goes through the focal point. If a ray goes through the center of the lens, it moves continuously. These are the two rules that you have to follow. So when drawing this, you have the image, object. You draw this line, then you draw this line. Now your eyes receive these two lines. Your eyes doesn't have a brain. So he thinks that these rays get together at this point. So he thinks that the image is here. But again, it's an illusion. This is a virtual image. This is a virtual image. And if you keep it at the focal point, the image will be formed at infinity. And if you keep it between f and 2f, image is formed away than 2f. Clear? You just have to follow the rules, okay? Just follow the rules. What are the rules? You have the lens like this, center line like this, center line like this. This is your focal point. This is 2f. Then again, this is your focal point and this is 2f. You keep something here. What are the rules? Draw the basic lines that you can draw. If something goes parallel, what happens? If something goes parallel, they goes through the focal point. First rule. If something goes parallel, they goes through the focal point. Clear? And if something goes through the center of the lens, they moves continuously. They moves continuously without any refraction. Now these two rays get together at this point, so the image is formed here. Now these rays get together at this point, so the image is formed here. Clear? That's how the image is formed. Clear? Just follow the rules, okay? Just follow the rules, set of rules given. So I'll let you know the date for electronic session. Most probably it will be Tuesday morning. So likewise, you can draw all the images. And you have to remember these things. So sometimes the image is virtual. In the first scenario, image is virtual, right? It's just rays deceiving your eyes. But here rays are actually meeting, see? So it's a real image. Here rays are actually meeting. So it's a real image. Here rays are actually meeting. So it's a real image, see? Sometimes they are virtual, sometimes they are real. Sometimes they are upright, sometimes they are inverted. Okay? So remember those things. And concave lenses, okay? Concave lenses, they always form a upright, smaller image. Upright, smaller image. Clear? Upright, smaller image. They always form upright, small image. Clear? Concave mirrors, concave lenses. So that is the whole idea about lenses. So there's something called principle of reversibility of light. It's good to know this thing. What is the principle of reversibility of light? Go through this path. Here your light ray goes through this path. And if you send a light ray in this path, it will go through this path. Here your ray goes in this path. And if you send an opposite one, it will come through this path. So if light rays go through a certain path, it can return through the same path. Clear? That's the reversibility of light. Clear, everyone? That's the reversibility of light. Clear? Did you understand that? If there's an optic system like this, if the light ray goes like this, then if that light ray returns, it will come through the same path. If that light ray returns, it will come through the same path. That's what we call the reversibility of light. Aloke pratyavartata mooladharma. Clear? Did you understand that? Everyone, do you need any more clarification related to the reversibility of light or just mention in the Zoom chat? Did you understand? Zoom students and the YouTube live students, just mention quickly. Others, just mention in the Zoom chat. Nice, nice. So one question number 6. Actually, when they write ambulance in ambulance, it's not actually upside down. They invert ambulance. Why? Why do they invert ambulance? When they write ambulance in front of ambulance, when they write that, they invert it and write. Why? Quickly mention the answer. Someone quickly mention the answer. Why do they invert the term ambulance? When they write ambulance in front of ambulance, why do they invert? Does anyone know? Why do they invert the term ambulance? Yes. Usually when an ambulance is moving behind you, you see the ambulance from the mirror, right? Whenever you are driving, whenever you are driving, you don't look like this, okay? You don't rotate your head and look like that. Then you will need another ambulance, right? So whenever you see the sound of ambulance, you look through the mirror. And mirror inverts everything. Mirror inverts everything. It laterally inverts everything. Here. So then if they write ambulance correctly, from the mirror you will see an inverted ambulance. But if they invert it in front of the ambulance, if they invert and write on the ambulance, then from the mirror you will see the correct term. Clear? From the mirror you will see the correct term. That is the idea. Clear? Following are some facts. Question number 4. We'll see question number 4. Following are some facts about total internal reflection. Light must travel from rare medium to dense medium. Can someone mention the answer? Question number 4. Question number 4. Anyone? Quickly try to get an answer. It's available in your tube. Some students are telling 2, some students are telling 4. Following are some facts about total internal refraction. Light must travel from rare medium to denser medium. The angle of incidence must be greater than the of the two medium. Greater than the, it should be greater than there's a printing mistake. The angle of incidence must be greater than the critical angle of the two medium. Must be greater than the critical angle of the two medium. Then give me the answer. Small change. So it's true, right? Sorry, it should move from a denser medium to rarer medium, right? For, I mean, for total interrefraction to happen, you should see when you send a ray, if it moves like that, if you increase the angle, then it will if it will face total internal reflection. But when you send a ray like this, if it moves like this, then the total internal reflection will never happen, right? So, what is this difference? When you move from a denser medium to a rarer medium, when you move from a denser medium to a rarer medium, angle increases. When you move from a rarer medium to a denser medium, angle decreases. So, this total internal reflection can happen only when it's moving, when the angle is increasing. So it happens only when the ray is moving from a denser medium to a rarer medium. So that's the correct one. And at the same time, you should pass the critical angle. Angle should be larger than the critical angle. Then only it will reflect internally. Did you understand? Did you understand the concept? Did you understand? Can you please reply? You know this concept, dense and rare, right? When the ray moves from a denser medium to a rarer medium, it moves away from this one. When a ray moves from a rarer medium to denser medium, it moves towards this perpendicular line. So this total internal reflection can happen only when it's moving from a denser medium to a rarer medium. Clear? What about this question? The place where the light source should be kept in front of the concave mirror to send the light beam to a long distance. It's a nice question. Why? Some student, I saw that a student asked me a use case of these concave mirrors and convex mirrors. Lighthouse, you have a mirror, you have a bulb, then this bulb, the rays from the bulb is catched by the mirror and mirror sends these rays out. It's a very nice use case. Lighthouse uses a mirror. All lighthouse uses a mirror. Then it's same here. In a lighthouse, we keep the light, and where should we keep the light? So that this lighthouse, this mirror can send these rays to a very large distance. To a very large distance. Where should we keep the light? Very large distance means infinity. So how can we send a signal to the infinity? In a concave mirror. In a concave mirror. In a concave mirror, you should see if you keep something at the focal point, see, if you keep something at the focal point, that will go up to infinity. See, that will go up to infinity. Infinity is a very long distance. So when you need to send something to a very long distance, you should keep it at the infinity, at the focal point. So in a lighthouse, what happens is you have a concave mirror, you keep a bulb at the focal point. Then this mirror captures this light and they send them to infinity. That's why ships far away, maybe kilometers away, still can see the lighthouse. Why these rays are sent to infinity by this concave mirror. See, a very nice example from a very nice question. See, is that clear? Is that clear? See, that's the basic idea of that question. So you can try other questions, and if you need more questions or anything like that, you can inform me, okay? And I'll let you know about the electronic session. Please put your feedback in the Google form. And if you need any assistance related to O levels or A level subjects or anything like that, you can contact me. You can contact me through this number. Not 7781507003. Or else, if you can't contact me, if I miss your message, you can always contact my coordinator. And there are also students who did A levels very well. So, anyways, you can get any support related to O levels from them. Not 70. This is my coordinator's number. 402 9701. You can get any assistance from them. You can ask for any assistance from them. Okay. So I think today's session was useful. And like if you have any doubts, let me know. Mention in the Google form. And yeah, I think that's all for today. And I'll let you know about the electronic session and single medium sessions and all. Just let me know. Ask your friends whether they need a single medium session too, and let me know. Let's do it that way. And thank you for joining. Have a nice day.